Good morning, guys. Today we're going to talk about Green's theorem. Green's theorem is the relationship between a vector field and a line integral. But before we go there, we should talk a little bit about who George Green is. Now, George Green received no formal education except about one grade of school. George Green was a miller, and he kind of after his father died, he took over the business. He would meet his wife, Jane Smith, and together they'd form a partnership working with the mill, and eventually they would have 7 children. Now, Green would put together a treatise on electromagnetism where he introduced Green's theorem. At first, Green didn't want to publish that in any scientific journals because he was just a miller. He had no formal education, and he didn't believe that what he really was offering, how that would be taken with the scientific community at the time. But Green would have obviously great success, and eventually his paper would find its way into the scientific community. And he would go to Cambridge, eventually getting a degree, and then unfortunately he would die young. But let's get into what is Green's theorem. So if we consider, let me just go down here. Sorry, guys. There we go. So if we consider this path here, and we consider a counterclockwise path around it, in a vector field that doesn't have a j component, where the j component is 0. So that vector field just has an I component. So it's just going to be within that x direction. We can represent what's called the line integral as the integration of the path c, which is integrating p, which is pxy dot dr vector. Now the dr vector is really just dxi plus dyj. But we know that dyj is going to be equal to 0. So we're really getting the line integral, which is given below, which is going to be right here. So now basically what we can do is we can take a deeper look at this by breaking up the paths. So and looking at what's going to be considered the minimum and the maximum values. So if we look here, this would be the bottom path here. And what we'd be doing is we'd be integrating this thing from a minimum value of a to a maximum value of b. So we're kind of getting this function for the lower path, which would be y1 of x. So we can take that y1 of x now. Hold on here. We can take that y1 of x here, and we can kind of put it from a to b. So what we would do is we'd have it right here. So this would be p of xy, but now what we're doing is we're plugging in y1 of x, and we'd get dx there. Now, as far as the upper path goes, we can take that upper path from b to a, and this is the counterclockwise direction here. And the function that represents this would just be a y2 times x. And again, we can do the same thing here. What we can do is we can plug that in, as you can see here, and get x and y2x. I think the other one was up on top there. Oh, there it was there. Sorry about that. So we were plugging in for y, the y1x for the lower region there. Or that path, I'm sorry, not region, for that path there. So as we can then kind of put it all together, and so we can combine these two. We combine the top path with the lower path, and what we're going to do is we're going to get here that c, that line integral c is going to be equal to c1 plus c2. And as we put it in here, since we're integrating from a to b, what happens is 1 was from b to a, so if we just make that negative, we can have it from a to b. And then we'll get c is equal to c1 plus c2 for that line integral. Now we can rewrite the right-hand side as the function pxy from a to b. Okay, and we just realized that what we're really doing is, since we're plugging in those values, we're just going to run them along that interval there from y equals y1x to y2x dx. And that can be rewritten, because if we think of what the integration here of pxy, if we use a double integral, then we can actually use an integral of dp over dy. And if we do dp over dy and we integrate dp over dy, we actually just get pxy. So that allows us to kind of simplify this a little bit better right here, as you can see. And we're going to get the interval from a to b, and then what we're doing is we're going to get that interval from y1x to y2x of dp over dy dyx dx. Okay, so what is that? And what we're kind of generally doing is we're kind of taking a look here, and we're looking in the plane now, and this is your line interval down here, and that dp dy is actually the height of that line interval. So after we integrate that, as you can see we're doing over here with this double integral, what we're generally getting is we're getting a volume here. This is what we're getting with a base area called region R. So we can kind of take a little step back then, and we can go back to what we originally had, which was our line integral here. And so what we're really doing is we're doing an integration of our region, or our area, right, of dp dy. Now that there gives us 1/2 of Green's theorem. And so basically the line integral is going to be equal to the integration of the region, which is going to give us a volume, okay, in that particular direction. And remember, that was strictly in the I direction. In order to form Green's theorem, we have to go a little bit further. We have to actually consider the j vector direction as well. So we would kind of come down here, and we would do the same thing. We would create that same path that we have now, but we're going to be looking at that with the vector field in the j direction, where the I now is equal to 0. And what we get is working through the same methods, we're going to come up with p of xy dx is going to be equal to that region again. You know, and we're going to integrate that height dp dy with respect to the area. Now the derivation that we get here is, you can kind of see here what we're really doing here. So we're doing the vertical now. So we got q of d dot dr, which is going to be equal to that line integral q xy dy. And what we're doing is we're looking at a minimum in the y direction of A and a maximum in the y direction, which is B. And we're taking and breaking it up into two parts here. And really it comes down to the same thing. This one's positive though, and if you work out the derivation of it, you see that. And we get the line integral is going to be equal to the integration of that area, which is going to give us that volume. Okay. And if we come down here, we get, if we put it all together now, we put the I direction and we put the j direction together, what we get is we get that line integral, right, is going to be equal to the double integral of the region, which gives us the partial derivatives of dq over dx, or dq or q with respect to x, minus p with respect to y dA. And really that's it, guys. So if you go back and if you want to like get some examples and some experience with numeric values, you can always go to Khan Academy, and they have some really good examples there. And that's it for today. Thanks, guys.